Now if y is much less than L, then our equation, now our logistic equation, remember we're trying to relate this form to this equation, and our k is going to have different characteristics for these two functions. But if y is much less than L, then we can write y prime equals ky times L minus y as kyl times 1 minus y over L. Now, this form does not depend on y being much less than L. This is clearly equivalent to this for any value of L. But we can now say that 1 minus y over L is approximately equal to 1. Again, provided y is much less than L. If y is much less than L, then y over L is a small fraction and it's close to 1. In this case, we can write y prime equals KL times y. And this being close to 1, we can just leave it off. Again, this only applies if y is much less than L. Well, instead of writing LK, we could just use a single variable like r, and we can say that then this is very much like the equation y prime equals ry, which is not an uncommon form for exponential growth. I've used the form y prime equals ky, but this is y prime equals ry, so that as long as y is much less than L, y prime equals ry, so that we can rewrite the equation in the form y prime equals ry, where r equals kl. Y remains much less than L. And this function just has solution, and this solution should be very straightforward to you. This should be y equals y naught e to the rt. And that's identical with the solution we found previously. I'm not sure I have that handy, but well, let's just remember that our solution was y equals y naught e to the klt. These are identical, except that now we're using r. Well, this motivates us to go back and look at the form that we used for the logistic equation. A very common form of the logistic equation in textbooks and in writing would be this: y prime equals ry times 1 minus y over L. Now, this is identical to this equation, okay, with r equal to kl. And this equation did not depend on our assumption that y is much less than L. Everything that follows from this step down does depend on y much less than L. But this equation holds, and this equation is just a simple rearrangement of this equation, so that the common form, a common form, of the logistic equation is what you see here: y prime equals ry times 1 minus y over L. This does have the advantage that r is your initial growth rate. As long as y remains much less than L, this factor can be ignored, and we have exponential growth with which you're familiar. As y gets closer and closer to L, y over L, what happens to y over L? Well, as y approaches L, 1 minus y over L approaches 0. Because y approaches L, y over L approaches 1. 1 minus 1 is 0. So that this type of exponential growth that we started with ceases. The growth rate approaches 0, and our function levels off. And if we choose our constants and our integration constants correctly, we're going to get exactly the same results we did. And the steps of solving this problem are exactly identical, exactly parallel to the steps that we used in solving the problem with the form y prime equals ky times L minus y. We could even multiply through by L here, by L over L, and get this into the form y prime equals ky times L minus y. We're going to have to deal with y over L term, and the y term is simpler here than it is here, but the trade-offs are pretty even, and this equation can be solved by separating the variables. We're going to get dy over all of this stuff equals dt, and the entire solution is going to follow just by very, very similar steps, just with slightly different notation.